When we last spoke, I showed you how the input stage was calibrated, and I made a promise that sometime in the future I would show you the results of that calibration. Well, the time has come to make good on that promise. This is a dry well calibrator. It has a heating element and 5 different temperature sensors mounted in it. With this, I can set the temperature to a specific value and compare the measured temperatures with different sensors. The temperature loop is controlled with Recore using Clipper and plotted in Octoprint. The reference temperature element is this SDL model S385 platinum resistance thermometer. It has a reproducibility of 0.02 degrees Celsius, which sounds really good. If I send a milliamp of current through these wires, I can measure the voltage across these wires, and based on what I measure, I can calculate the resistance of the element, and from that deduct which temperature the end of the spare has. Now, this came off the internet, and it's a bit of a mystery. It was last calibrated in 1999 by Johnson Controls Calibration Laboratories, but the certificate was missing. I tried to track it down, but they told me no, it's too old. There were also 2 numbers written on a piece of paper and an older date. C equals 107.7888 and Z equals 0.3891. Those numbers are curious. That C could be the resistance at 20 degrees, and the Z could be the slope, as in the change in resistance in relation to the change in temperature. So with that assumption, I'm going to try to calibrate this. I measure 99.9894 ohms of resistance when the PRT is submerged in melting ice water. This is well within the specification of 0.05 ohms. Then I measure 138.6283 ohms when the PRT is submerged in boiling deionized water. And because I have a barometric pressure sensor, I can use the Clausius-Clapeyron equation to calculate the boiling point of water here in the crow's nest at 100.437 degrees Celsius on this sunny day. Logging the temperature at 20 degrees and its derivative, I'm getting 107.7821 and 0.3884. Those numbers are relatively close to the numbers on the paper, but it could also be a coincidence. For all I know, that's just the preferred tea temperature and ratio of milk to sugar the previous guy had written down. My thermometer is off by 0.07 degrees C. I can now measure the temperature of all the different sensors on Recore and compare them with the reference. At room temperature, 3 sensors are off. If I measure the temperature at different levels, I can see that the Thermistor is pretty close to the reference at 200 degrees. But the thermocouple is still too high and the PT1000 is still too low. Let's start by fixing the thermocouple. That has an interesting issue. I'm using the values taken directly from the calibration of the board, and what I'm seeing is that the temperature is 16.1 degrees too high at room temperature and 16.8 degrees too high at 200 degrees. That tells me that the offset is wrong, not the gain. During calibration, I measured the offset at around 0.65 volts, but I had programmed it at 0.7 volts. I didn't think of it much at the time, but in hindsight, I should have been more careful. The reason for the error was assuming that the ground plane on the board being tested was the same as the ground plane on the bed of nails, but a current was flowing through the nails, and this caused a voltage drop across them, which led to the error. The solution was to measure the difference between the ground planes and subtract it from the measurements. The PT1000 and the Thermistor are showing different symptoms, but in fact the reason for the error is the same. Thermistors used in 3D printing are usually type NTC, meaning that they have a negative temperature coefficient. As the temperature goes up, the resistance goes down. When used in a voltage divider, a higher temperature will lower the output voltage, and this is significant for the further discussion. A PT1000, on the other hand, has a positive temperature coefficient and also changes much less. As I discovered, the reason for both errors was twofold. Reason 1. In order to use the input for both thermistor and thermocouple, a fixed but programmable offset was added to the input. When turned off, the offset should not influence the measurement, but it did. The impact was easy to model in SPICE and then transferred to Clipper. The results show a slight improvement, but even with this issue out of the way, the temperatures were still off. Reason 2. And this one was quite a pickle. After some soldering, I was able to narrow the problem down to the choice of the TVS diode on the input. Looking at the datasheet, I discovered that the reverse leakage current was enormous for the 5V TVS diode. We're talking nanoamps here. So I set up another experiment for testing the reverse leakage current at different voltages, did some linear regression, and came up with a cubic fit that matched the curve well. Adding this to the code, I was able to get some great results, finally. But this would probably not be accepted in upstream Clipper and is very complex from a calibration standpoint. So I fixed it.
One revision later.
This is revision A6 of Recore. It's mostly the same, but it has a couple of improvements. The new revision has an on-off programmable offset that is fixed at 3.3 volts, and the pull-up, the op-amp, and the ADC all have the same reference voltage, which simplifies the calculations so that the upstream Clipper implementation can be used. Now, there's still a TVS on the input, but one with significantly less leakage current. Insignificant. But the board can still withstand a zap from a cell phone from the 80s. I've also changed the testing jig so no current is flowing through the calibration test pins, which eliminates the need for the offset subtraction. So repeating the experiment from the previous revision, the temperatures are now all in agreement to within a degree. The reason why the temperature of a nozzle during a 3D print is important is that of repeatability and accuracy. If you have one printer, you can dial in the temperature based on trial and error. But if you're having trouble with the prints, it can be hard to diagnose the reason when comparing to others with the same setup if you don't trust the value displayed. I hope these hardware and software changes gives you confidence in what you're measuring, and let's move on to speed tests.